Hi everyone, today I want to talk about distributed computing. Recently I was at the Cloud Native conference where I talked to a bunch of people about containers, virtualization, Kubernetes, and distributed computing, and I realized that everyone had a slightly different entry point. People had misconceptions about how things came to be, and since I've been around the block for quite a while, I figured out I will just create something that will show how distributed computing came to be and where we are now, so that the newer technologies like Kubernetes, containers, or other virtualization technologies make more sense. So this video has a companion blog. So I wrote it right here, from physical servers to virtual Kubernetes. You can read it. I'll put a link in the video description. We're not going to go through the whole blog. I made some of the blog elements into the presentation, and this is going to be a little bit easier. So the first thing is easy, computer, right? Everybody has it, whether in your pocket or on your desk or as a laptop. Computers in the olden days were super big and not affordable at all, but for the personal computer, the process is very easy. We have us, users, executing a program, and the program does stuff, returns results, or what have you. So I am currently running Pop! OS Linux, but I thought it would be fun to actually show how we can run something else. In our case, we're just gonna do this on Windows. So you can see I have here an actual Windows system. This service called copy.sh enables you to run almost any old operating system inside of your browser. So let's figure out if we can make the screen a little bit bigger. I don't see a way how to do it. Oh, go full screen. All right. So yes, this is Windows 2000. I definitely remembered it. I am guilty of using it, and I'm sure a lot of us also remember it as well. So you can click start. You can do whatever you would normally do. We can go to settings, control panel. This is as slow as normal Windows, so nothing changed here. And we could see our Java plugin little guy. I remember this one. And we can just change various settings and do all Windowsy stuff. So a little bit of a nostalgia trip. But whether it's Windows, whether it's BSD, Linux, anything else, that's just a single physical computer and the user doing stuff with it. It doesn't have to be a desktop. We can also have a server, but the principle remains the same. So those are physical computers. Now, let me go back to the presentation here. Sorry for all the clicking. All right. So a while later, we have networking. So networking solved the problem of single computers being limiting, as in nothing can talk to each other, we cannot exchange information, we cannot even run web servers and so on. So networking is something we take for granted. Everybody uses it constantly, but at the beginning it was something really unique and novel. So typically we would have us, a user, issuing a request to something like a web server using our web browser in our computer, and then it contacts the web server. This might in turn contact a database server. There might be a worker process on a separate server. So suddenly we have all kinds of networks being connected to each other. So that's the next obvious step in the distributed computing. So let's see how those networks could work. I have here my home lab, and when I execute this command, you will see the output of it in a moment. We're going to grab nodes from my home lab, which is just a server, and it consists of a few virtual machines, and we will see how they talk to each other. So there we go. We have 3 virtual machines, and I can ping each machine from each other machine. So we are connected, we are networked, and that's the basic principle of doing any kind of networking. You can connect machines together. Now, obviously, networking is extremely sophisticated with various protocols and a lot of stuff flying around. but the basic principle remains the same. I want to be able to send packets of information from one location to the other reliably through the network. So networking was great, but networking on physical servers is limiting. And to be more precise, the physical servers were limiting. So VMware and other companies before it came up with the idea of virtual machine. Again, now this is something we take for granted, but this is a quite interesting invention. So virtual machine makes it so that using a software called hypervisor, which has type 1 and type 2, we can essentially emulate a computer in a computer. If you're a tech savvy, you will laugh that this is obvious, but again, this wasn't obvious back then, and this is a very important milestone in the journey of distributed computing. So we start again with the user making the same HTTP request, but instead of this request hitting a physical server, it instead hits a virtual machine, sitting maybe on a single physical server or sharded servers, where you can hit your web server, your DB, and then in turn, all those calls are being routed to the hardware via hypervisor. It was a super important idea that essentially completely revolutionized how we consume compute and gave rise to all cloud providers as we know, AWS, Azure, Google, Civo, you name it. All of those use virtual technology, virtualization technologies in one form or the other. So how does it look like? We've seen it earlier, but one more time. This is just 3 virtual machines running on my small Geekom server. If you're interested, I recently released a video about my home lab and how you could set up yours as well. I'll link the video in the video description. But that's it. Those are virtual machines. They run on actual single small server here, and I have 3 virtual servers out of 1. So virtual machines were obviously really good invention, and everybody loved them until we realized that they are too slow. So industry and users demanded more performance out of the current hardware, and virtual machines take time to boot, they take time to set up, and they are also relatively slow to execute because we are packaging the whole system. Kernel, all the system components are virtualized as well. Only the hardware is accessible through the hypervisor. So a little known company at that time, Docker, came up with this idea of packaging application into something that the application would consider as a fully operating system, but from the outside, it would be just bare bones, few components and processes running in an isolated Linux namespaces. So our journey starts the same. We are the users, but now instead of talking to a virtual machine, we are actually talking to a container, which is a very, very small subset of libraries and apps and a little bit of networking that serves our requests. Then this container might call another container, or we might call system resources. The difference here is that instead of having hypervisor to manage all the calls, we actually have a shared kernel and a shared hardware. So we have much more system resources that are shared rather than abstracted within a virtual machine. This was great. Now we all like and use containers every day, whether we know it or not. A lot of the services that we are using, whether those are SaaS services or popular apps, behind the scenes run in containers. So with this small demo, I want to show you how quickly it is for a container to be created and to be driven down. And we could imagine that those are mini servers. I want to be careful with that. They are not like VMs, not like servers, but from outside, they kind of look like it. So let's run the command. And you can see that we have created 5 little containers. They were up for about a second. They executed a simple command, just staying up for a moment, and then they were destroyed. The virtual space they occupied was about 52.8 megabytes each, and then the actual size loaded to memory was even smaller. So this obviously, those are containers that don't do anything. They just start Nginx Alpine image right here. Containers can be much larger and do significantly more complicated things, but this is just to exemplify how quickly, compared to virtual machines, those can be brought up and destroyed, which was one of the main points of having containers in first place. This and the fact that they could package each application in exactly the same way. Now, a little later, at Google, from Google, we got something called Kubernetes. Before Kubernetes was released to public as an open source project, Google was using a system called Borg, which internally scheduled containers. So that's essentially what Kubernetes was invented for. Imagine you have a lot of those containers everywhere, thousands, if not millions of various containers on various machines, virtual machines. It's very hard to reason about them at such scale. So we needed a tool that could help us orchestrate containers. What does it mean to orchestrate a container? Things, for example, like deciding on which node or virtual machine should the container run. How many copies of a given container should be present at a time on each node? What should happen if a container should be killed? Should it be restarted or not? All those things and more is something that Kubernetes initially provided. Now, Kubernetes is a complex topic. It is a very sophisticated distributed system that was originally designed to orchestrate containers, but nowadays, with additions of a few important APIs such as CRDs and plugins, it can do much more. I don't want to confuse you further, but I will release more videos about Kubernetes and its superpowers, because I think at this point it became ubiquitous and boring in a good way, but you would be surprised how much of the infrastructure that we use daily Kubernetes powers. So given our example, we start again. In this case, we create a simple application. We communicate with various Kubernetes components. Specifically, we communicate with Kubernetes API server that in turn orchestrates the creation of our application through various steps. And at the end, our application lands on a virtual machine that Kubernetes manages. We can, of course, influence through configuration a lot of it, but suffice to say that Kubernetes orchestrates the containers that we've seen earlier, it being its main purpose. Again, it can be used for several other exciting purposes, but that was the main idea, and that's what Kubernetes is used for nowadays. Of course, Kubernetes itself introduced all kinds of problems, as every time when we introduced the layer of abstraction, we were getting new problems. Before we talk about those, let's do something a little bit more interesting with Kubernetes. So you can see here, we are going to execute a few commands. Again, we're going to get the nodes, and we will create a simple demo application, and then we will see if this application is running. So yes, we are creating application. I'm not going to go in super detail what it does. Suffice to say that this is akin to creating a web server on the virtual machine, or a web server container that we can now interrogate and look at in our cluster. So let's fire up my favorite program, which is K9s, which enables us to see various Kubernetes resources. This is my home lab. You can see I am running 0.33.4, and those are various pods that I have. This video is not about Kubernetes, so we're not going to go in detail here, but you can see there's all kinds of interesting things happening. and all those pods are running one or more containers. Remember, we talked about containers. Kubernetes manages those containers. All right. So with Kubernetes came another challenge, namely, how do we make this available for various internal and external use cases? So since we have a big Kubernetes system consisting of multiple virtual machines that run various containers effectively and orchestrate them, maybe some of those applications should be accessible only by certain teams or by certain individuals. How do we solve for this multi-tenant world? That's where systems like vCluster come in. vCluster is a class of systems that essentially is like meta Kubernetes. It virtualizes certain Kubernetes components to make it easier in this multi-tenant scenario to take more value out of your Kubernetes installation, to make it easier for platform engineers and other professionals to work with the Kubernetes host cluster. Whether this is managed Kubernetes or on-prem, tools like vCluster open up those different scenarios. So how does vCluster work? In a nutshell, imagine that you have several teams inside of a company, and each of those teams need to do something in Kubernetes. At the end of the day, they have either an application or part of infrastructure or a process that Kubernetes needs to host and orchestrate. Very quickly, it becomes obvious that we are torn between usability, cost, security, ease of use. Those concerns become real, and there are a few ways to solve them in Kubernetes, but Kubernetes by design was not created as a multi-tenant system. It was created as like you have to host something on Kubernetes in order to maximize the resource utilization and the orchestration of existing containers without too much thought put into how the multi-tenancy scenarios would play out. Kubernetes, of course, supports multi-tenancy. It has primitives for it. For example, it can isolate various workloads using namespaces and other things, but those things are not sufficient. So imagine that you have those small pods that you've seen earlier that are only accessible for specific teams. For all intents and purposes, from the outside, it looks as if this team or this individual has access to a fully fledged Kubernetes. I hope you see a thread that is very similar to virtual machines and containers. Containers look like virtual machines from outside, or for the applications that runs inside of it, they are indistinguishable from virtual machine, but they are not really virtual machines. Very similar historical concept could be applied to the relation between Kubernetes and virtual clusters, which is virtual Kubernetes clusters. All right. So here are some benefits that vCluster brings to the table, but let's focus on some cool commands. It's very easy to create a vCluster. Let's kick it off real quick. While this is happening, let me explain why this is important. I hope you can see a pattern of a trend of adding new abstractions that are slowly arising as the need when community and individuals start using certain technology and explore its boundaries. The more the use cases grow, the more people realize that there are certain things that are missing or certain things that are not exactly optimized. So in case of Kubernetes, it was the multi-tenancy, the cost, the rigidness that came from just everybody using kind of the same system, and the need to split this into smaller pieces without just creating new host clusters, new Kubernetes clusters. This is what brought vCluster to be. But this same analogy can be extrapolated to other technologies such as AI nowadays or others. All right, so we have created this virtual cluster. So now we can connect to this virtual cluster and just get some info how this virtual cluster looks like and what is inside of it. So the connecting is really simple. We are pointing it, and now our Kubernetes has essentially a small Kubernetes inside of it. We can create the same deployment as we've seen earlier. You can see this now creates a container. The difference is that this Nginx pod is now running in virtual cluster, not inside of the host cluster. If you haven't worked with vCluster earlier or similar technologies, it might be super confusing. I encourage you to check out some of my other content or check out my talks or workshops I give regularly about vCluster, or just check the vCluster docs and learn about it if this is something that you think might benefit you. So now we are using this specific context. We don't have any resources ready yet because they are still being deployed, but that's fine. So let's see if we can connect to it and get some pods. All right, so we were able to connect to our vCluster, which means that our configuration puts it there, and we can see we have those Nginx pods. The reason why we don't see them in the last command is that they are not running in this namespace, they're running in the default namespace. But they are here, and we can definitely see them. How to delete virtual cluster? Super easy, and something that is also very valuable. We can just simply execute the delete command or delete a Helm chart, and we do not have to deprovision the host cluster or manage clusters, which is complicated, especially if you run your own bare metal cluster or a cluster on bare metal server. So with this, our virtual cluster is gone, and we are back at the original state. So I want to finish this video by talking a little bit about the pattern, because I believe that there is a lot of value in reaching back and looking at how things progressed from very early days of computing, where there was just a single physical machine, to the first moment when they were connected. Each time, each part addressed and solved certain problem, but also made us aware of its limitations that led to the next big discovery. So the physical VMs, physical computers moved to VMs because they've solved the problem of stranded resources and isolation, essentially. It was extremely difficult to provision things and just work at any scale. When the VMs were created, quickly became obvious that they are too slow for the growing needs of industry and users. So heavy OS problem was solved by creating containers, but in the same time, containers introduced orchestration chaos. There were so many of them. They often came in pairs or in multitudes together, and something needed to manage them. So then we created Kubernetes to deal with that, which solved this problem by introducing orchestration. When the orchestration was there and the big Kubernetes systems came to be, it became clear that multi-tenant and kind of sharing those Kubernetes resources is something that needs to be solved, and that's where technologies like vCluster came to be, that introduced control plane virtualization and helped us reuse this much better. But this in turn introduced another layer that might be solved with something else in the future, or tools like vCluster might advance and solve the problems in this space. The reason why it's very important to look at the computing space like this is mostly because of the current AI revolution. This technology seems to be taking the computing space and society by storm. Everybody's talking about it. There's a lot of news and a lot of uncertainty, but it's not in isolation. This technology came from somewhere and is going somewhere. It came to fulfill a certain need, and it will create its own limitations, like hallucinations, for example, or consuming vast quantities of compute for training and other limitations. So thus the cycle will continue and new abstractions will come to be, and everything will go on this way. I hope that's what you get from this video, and you can look at the pattern of distributed computing and a brief history of it, and realize how those things come together, and how tools like Kubernetes or virtual clusters and others solve problems that the previous abstractions introduced. A little bit of URLs, as always. Here is the URL to the blog post that I talked about. I also created an interactive scenario in Killer Coda that you can do yourself and learn about vCluster a little bit more, or check out vCluster GitHub repository. So that's it for today. It was a little bit different video from usual terminal content, but I really felt it's a valuable piece of information, especially now when everything is super fast and people have short attention spans and AI does all our work. So having a little bit time to reflect on the history of distributed computing and connecting the dots this way, I hope is valuable. This being said, thanks again for watching, and see you guys in the next video.